Yes, hello. Welcome again to our channel. And today we are moving from the regular season MIT Integration B polynomial questions to the quarterfinals. So I extracted all the problems that involve polynomials in the quarterfinals of this year, 2023 Integration B quarterfinals. The first problem was from quarterfinal 1, the first problem, and that was the integral of x to the power 4 times 1 minus x to the power 2 over 1 plus x squared, and that was from 0 to 1 interval. Then the second question was from quarterfinal 2, quarterfinal number 2, the second problem, which was the integral, it's an indefinite integral of 1 minus x over 1 plus x squared times x to the power 2 over 3. And lastly, question 3, this comes from quarterfinal 3, the first problem, which was the integral, and this is a new one, of the residual between the actual value and the floor function of the function x over 2 to the power n, summed from n is equals to 0 to infinity. Sometimes this function is referred to as the sawtooth function, and we'll see why it's often referred to as that way. So again, I would like to remind you that please subscribe to our channel, and this allows you to get these notifications when we come up with solutions, but also it helps us to gain some level of notoriety or some level of visibility. Thank you very much. And so we go next to the as we mentioned, the first problem comes from quarterfinal number 1. That was problem 1, which is the integral of x to the power 4 times 1 minus x squared over 1 plus x squared, integrated in the interval 0 to 1. So what I would do, I would just expand out 1 minus x squared, and therefore I get 1 minus 2x plus x squared, and then I multiply by x to the power 4, and so I obtain x to the power 4 minus 2x to the power 5 plus x to the power 6. Then I'd go ahead and do long division. So I would flip around so that the highest degree comes first, and then the lowest degree comes last, and the same thing I would perform with the divisor. So the dividend and divisor I flip so that I have the highest degree come first. And so x to the power 6 minus 2x to the power 5 plus x to the power 4 divided by x squared plus 1. Multiply the divisor by x to the power 4, and therefore I get x to the power 6 plus x to the power 4. Subtract that from the dividend, and so the x to the power 6 and x to the power 4 terms cancel each other, so the only residual there is minus 2x to the power 5. So I multiply the divisor by 2x minus 2x to the power 3, so that we get minus 2x to the power 5 minus 2x to the power 3. So when that is subtracted from that residual, we are left with plus 2x to the power 3. So then I multiply the divisor by 2x, and so I get 2x at the power 3 plus 2x, and we subtract this from this residual, and we are left with only negative 2x. So this is value is lower in degree to the denominator. So this integral now is the same as x, the integral of x to the power 4 from here, minus 2x to the power 3 plus 2x minus this negative sign coming here, 2x over 1 plus x squared. Now this part here can be integrated easily. This part here would require some substitution. So going to the next, the first part, x to the power 4 minus 2x to the power 3 plus 2x, this can be integrated independently from this last component, and as you can see. So I've broken out these two integrals. The first part there can be integrated, so the first x to the power 4 term becomes 1 over 5 x to the power 5 minus this second term is the same as 2 to the power 2 over 4 times x to the power 4 plus the last part 2x becomes x squared from 0 to 1. And then we keep this last part the way it is, and when we substitute the limits we get 7 over 10 minus the second integral. Now focusing on the second integral, I will end up substituting x equals to tan theta, so that dx is equals to sec squared theta d theta. And so also changing the limits, when x is equals to 0 here, theta arctangent of 0 would be 0. And then when x is 1, the arctangent of 1 is pi over 4. So substituting in the new variables and the limits, we get integral of 0 to pi over 4 of 2 tan theta. So x, where x appears tan theta, where as you see the squared here now becomes 1 plus tan squared theta, and then dx becomes sec squared theta d theta. So as we know, 1 plus tan squared theta is the same as sec squared theta, and that now cancels out with this second sec squared theta in the numerator. And so you're left with 2, the integral, because I've pulled out the constant of tan theta from 0 to pi over 4. Now, for those of you who are well versed with this function, we know the integral of that is negative log of cosine theta. So with the constant, now we have negative 2 log cosine of theta. And since we have this negative sign here, the intervals kind of flip around. So we get 2 log cos 0 minus 2 log cos pi over 4. Now log 0, cos 0 is 1, log of 1 is 0, so this part here becomes 0. Now we're left with this last part, cosine of pi over 4 is the same as 1 over root 2, and since we have these 2 can go up here, so that this entire value under the log natural logarithm function is squared up, and then so we're left with negative log 1 over 2. Then getting the reciprocal of 1 over 2 to remove this negative 1, akin to just moving the negative 1 here over here, results in log of 2. So going back to our original problem, x to the power 4 times 1 minus x squared over 1 plus x squared dx, since we had integrated the first problem, which was 7 over 10, and then the second integral, we just found this answer as log 2. So the answer now is 7 over 10 minus log 2, and this is our final answer. This is our final answer. Okay. So our second problem comes from quarterfinal number 2. That is problem 2, and that's the integral of 1 minus 2x over 1 plus x squared times x to the power 2 over 3. I will look, the way I would approach this is a little bit tricky. I would express the numerator as 1 plus x, and this I'm trying to really mimic whatever is shown here in the denominator, minus 3x. And so this now becomes 1 plus x over 1 plus x squared, x to the power 3, minus, so I've separated this numerator into and denominator into two fractions, minus 3x over 1 plus x squared times x to the power 3. So the 1 plus x here cancels with one of the 1 plus x's in the denominator, and you're left with 1 over 1 plus x, x to the power 2 over 3, minus 3x, since this x divides with this x to the power 2 to the power 3, we're left with now 3x to the power 1 third, and then the denominator remains so. So if you look at this critically, this component here, this x to the power 2 over 3, is the same as 3 times the derivative of x to the power third, and then 1 over 1 plus x remains, plus, and as you can look at this second part here, this fraction here, 1 over negative 1 over 1 plus x squared, is the same as 3 times the derivative of 1 over 1 plus x. So it seems like we have a product rule under play here. Two parts of the product being differentiated one after the other, and then you have the sum of that. So essentially what this means, just pulling the constant out, clearly we're seeing something that the integral of this value is the same as just the product of 1 over 1 plus x and x to the power 1 over 3, and then with the constant. So plugging in the expression in place of what was provided in the question, as you can see, the constant being there, and then whatever is in the integral part here is just the derivative of one component over the other. So I could quickly deduce that the integral of this is the same as 3 times x to the power 1 over 3 over 1 plus x. And then obviously we've forgotten our big constant because this is our indefinite integral. And this is our answer. Now this problem is the most complicated problem, but the logic behind it is not super complicated. Question 3 is from quarterfinal number 3, and this is problem 1, which is the integral of the summation of x of the residual between x over 2 to the power n and the floor function of x to the power 2 over 2 to the power n. This is how that residual function is expressed. Sometimes we call it the sawtooth function, and I'll show you why it's called the sawtooth function. So for example, here plotting y is equals to x, and then I've also plotted y is equals to the floor of x, and as you can see, at every integer point it flattens out, and so when we get this residual, and that's the difference between the actual value and its floor function, as you can see, at every point where the floor function intersects the graph, it begins to be 0 by being 0, and then as you go up the difference increases, and then at this point the 0 collapses to 0 again, and then the difference starts increasing, and at this point again the difference collapses to 0, and the difference starts to increase again, and essentially how you would plot it is something like this. So the difference between the function as it deviates further from the floor function increases, and then when it hits the next integer, that difference collapses squarely to 0, and so on. And that's where we actually come up with the name sawtooth, because the function here looks like a sawtooth. So solving this integral would look something like this. So first of all, we get the summation of the actual function x over 2 to the power n minus the floor function of x over 2 to the power n. Now, this first summation, since x is not really involved in the summation, we can focus on the 1 over 2 to the power n, and using geometric series to infinity, since we're starting from 0, so by 0 it means that the first value is 1, we have 1 over 1 minus the constant ratio, which is 1 over 2. And so this results into 1 minus 1 over 2 is a half, reciprocal of a half is 2, so 2x. So we can quickly integrate that. So 2x is when integrated is x squared from 0 to 2 to the power 10. And so that means that it's the same as 2 to the power 20 minus now the integral of the summation of the floor function of x over 2 to the power n. Now, looking at 2 to the power 10, because when you go to, when 2 to the power n becomes 2 to the power 10, at the limit here of 2 to the power 10 in the x domain is when now you obtain the value 1. Otherwise, it's 0. So in the entire domain, 2 to the power 10 is 0. It only hits 1 at the very limit. So any denominator greater than 2 to the power equal to 10 to the power equal to 2 to the power 10 and above can be ignored, and so our summation now that ended up going to infinity now will become a summation from 0 to just 9, because these are the only values that would survive, otherwise the rest would just be 0. Looking at flow function, what a flow function is essentially a function that is constant between two integer points. So for example, between two integers k and k plus 1, x over 2 plus x over 2 to the power n in this regime means that the flow function is k, right? And so in that interval, it means that x is between 2 to the power n k and 2 to the power n times k plus 1. So we can go back to our integral here and say that, okay, we can sum up, because there are many strips indexed as k, but in each strip we integrate knowing that the value is just k. So as you can see, we are summing from k is equals to 1, and that's the first strip. And one important point I want to raise is that when we are focusing on x to the power 2n, x over 2 to the power n, we're focusing on that flow function, it means we're going to have 2 to the power 10, because that's the maximum value of x, divided by 2 to the power n strips minus 1. These are the number of strips, continuous, how do you call, constant value strips that exist when it is 2 to the power n, and that's why I have indicated here that we're having 2 to the power 10 minus n minus 1 strips, and in each strip we're integrating knowing that the value of the flow function is k. So we've already deduced the first part, which is 2 to the power 20, and then since the integral of k is kx, and then we see the limits to n, 2 to the power n times k, 2 to the power n, k plus 1, the difference there is 2 to the power n. So it becomes now 2 to the power 20 minus the first summation of n0 to 9, summation of k is equals to 1 to 2 to the power n minus 1, 2n times k. I can pull the 2n out and then just remain with the k inside here, and it becomes an arithmetic progression. And so as you can see, um, the sum of that arithmetic progression up to 2 to the power n to the power 10 minus n minus 1 is this value here. Now we can quickly see that this 2n can, this 2 to the power n can cancel with this n because this is the denominator, and then one of the 2's here can cancel with this 2 in the denominator, so we can quickly pull 2 to the power 9 out, remaining from dividing to the power 10 with 2, and then we're left with 2 to the power 10 minus n minus 1. Now this is interesting because as n is equals to 0, this is 2 to the power 10. When n is equals to 1, this is the same as 2 to the power 9. When n is equals to 9, this is the same as 2 to the power 1. So I can just quickly express this as a summation of 2 to the power j, from j is equals to 1 to 10. And now this is a geometrical progression. So we can derive this sum of that series with a constant ratio 2, which is now 2 to the power 11 minus 2 over 2 minus 1. And then obviously subtracting 1 10 times results in minus 10. So we have 2 to the power 20 minus, because 2 minus 1 is 1, 9 times 2 to the power 9 times 2 to the power 11 is the same as 2 to the power 20, minus this 2 to the power 9 times 2 is the same as 2 to the power 10, and then minus 10 times 2 to the power 9. Now what this means is that these 2 to the power 20s cancel out, and we're left with this positive, because we have two negatives here, 2 to the power 10, which can be expressed as 2 times 2 to the power 9, and then plus, because this negative and this negative become positive, times plus 10 times 2 to the power 9. So this results into 12 times 2 to the power 9, and this is the final answer. Great. Thank you again for paying attention and also listening to us. Again, a quick reminder to you that for those of you who have not subscribed, please subscribe to our channel. That just gives us that extra morale that we need to keep going. Thank you. Until next time.